Today we are going to discuss about transition graph and Kleene's theorem. So our objective is how to draw a transition graph and what its use. And next one is what is the Kleene's theorem and what is its applications. So first, if we're talking about a transition graph, we know that transition graph is basically a flow chart for an algorithm to recognize a language. Or transition graphs are pictorial representation of finite automata. So basically, transition graph contains a finite number of states in which at least one which is a starting state and some or maybe more than one are the final states. Next, a final set of input letters from which input string are formed. Means you have a collection of the finite words or finite letters that will be your input string. And third one is finite set of transitions that show how to go from one state to another state. That is the third point explained that transition function. That should be the transition functions. So that means a transition graph contains these three things. First one is the finite number of states. Second one is the finite set of inputs. And third one is the transition function. So in transition graph, there are few notations we are using. The first one is your state. So state can be represented by a circle. Next one is a transition from one state to another state. It can be represented by an arrow, from one point to another point. Third one is the starting state. So starting state always represented by the arrow which just come to meet the state. And next one is your final state. So final state is represented by the double circle. So this there are four types of the notations used in the transition graphs. So there is an example of the transition graph. Consider if you have to draw a DFA with the string 0, 1, and the DFA state that we have to draw a DFA which accept all the strings starting with 1. So first of all, we have to start the starting state. So this is your starting state. From here, you have to start. So we have two inputs. First one is the 0 and 1. So there are two transitions from this starting state. First one is for 1 and second one is for 0. There are the two states. And our next target is, because this DFA states that we have to form the string or the DFA which accept only 1. That means starting with 1. It's not starting with 0. So the state coming from P to T, this state, which are the coming from P to T, this state from P to T, this state be not useful for us. This state is not useful for us. So that's why this can become your trap state or dead state. So our useful state is this one only, Q state only, because our condition is we have to start from 1 only. So that's why the state Q can be useful. The state T is not useful. That is your trap state. So Q becomes your final state. So this is your the DFA which always starting from 1. So that will be acceptable by this DFA. This is the reject. Next, our objective is the Kleene's theorem. So what is the Kleene's theorem? So Kleene's theorem states that for any regular expression R that represent by a language L of R, there is a finite automata that accept this language. Basically, what Kleene's theorem is telling that? Kleene's theorem is telling that if you are having a regular expression, if you are having regular expression R, then you can form the language with that regular expression. First one. Second one is if you are having a machine, that means you are having any automata, that means you are having any automata. So you can also convert from this automata to that regular expression, or from this automata to, you can also convert from this automata to that language, L of R. So that means the Kleene's theorem is state that if you're having, there are three terms. One is your regular expression, second one is your regular language, and third one is your automata. That means the diagram, state diagrams. So if you're having any of these one, then you can convert from any one of these another one. So this is the basic Kleene's theorem. So first Kleene's theorem is state that if you're having a regular expression R, then it's a represent a language L of R. If it represent a language L of R, then you can draw a finite state machine which accept this language. And second one is it's state that for any finite automata M, so that accept a language L of N, there is a regular expression that represent the same language. Okay, so these both are same. If you are having a regular expression, then we can construct a finite automata, or if you are having a finite automata, then you can write a regular expression for that language. Next, so how can you prove this one? So first lemma, any regular language can be accepted by a finite state automata. How can you construct? See, if there are very basic input for any language, that is your phi, sigma means epsilon, or any small string, single string A. If any automata can be accept all these three, then that automata can also be accept the combination of all these three. How many times you can combine them, that can also accept. So basically the fundamental steps we are able to perform that fundamental step, so then definitely we can perform the combination of these fundamental steps also. So to prove this, we can construct the finite automata for the language phi, epsilon, and a small string A for any symbol alphabet sigma. So we know that if you want to construct a finite automata for L equal to phi, if you want to construct L equal to phi, simply just we construct a starting state, and this starting state becomes your phi. Next, if you want to construct the sigma, then that your starting state becomes your final state. So what is the difference between these two terms? First one is L equal to phi. That means you are not giving a single input, but this is the null string. Means if you're giving a null string to the as an input, so that's why your starting state becomes your final state, because that means without giving anything, you are just came at your final state. And third one is if you are giving very small input, that means a single input, that consider this is your A as a single input. So if it is start from S and give a single input A, and that becomes your final state. So if we are able to draw these three basic input for any finite automata, then definitely we can construct the combination of these three inputs. And we know that any language we want to draw, or any regular expression if you want to create in the automata, that should be the combination of these three only. So that's why the first step can be possible. Next lemma is state that for any finite automata M that accept the language L of M, there is a regular expression that represents the same language. So what is this? This statement is telling that if you are having any finite automata, that means if you are having any machine, if you are giving any machine, then you are able to draw the regular expression of that corresponding machine. This lemma is stated, and this lemma easily can be proved by the Agent's theorem, because Agent's theorem also state that if you are having a finite automata, you can draw a regular. How can you draw a regular expression? Agent's theorem also state that. So there are these two lemma of finite automata, and that was your transition diagram. So that's all about this lectures. So thank you very much.